What we want to do in this unit is to look at IPv4 addressing. The IPv4 addresses are the way that information actually gets from one location to the other. And we use the hardware address, the layer 2 address, to deliver the information to a specific machine. So with that, the objectives: distinguish unicast, broadcast, multicast addressing, and understand IP addressing schemes, including address classes, subnetting, classless addressing, and supernetting. CIDR is the / format instead of writing the subnet mask, and we'll look at both of those. Identify address ranges for private networks, and then configure an IP address scheme for a private network and configure IGMP multicast groups. Multicast, one of the things up here at the top, obviously, that we do. So we have these different methods of sending information from one location to the other. A unicast address is a one-to-one, one computer to the other, and if we're using a switch, only those two machines are going to see unicast traffic. So when we use unicast, we're going to have two computers. Should have little pictures of computers here, and they're going to communicate directly with nobody else in the channel, particularly if it's a switch and we don't have to get on the hub where we actually share the media. A broadcast, we're going to have a whole bunch of machines out here, and a broadcast is going to go to all of those machines so that they all get that information. Much like a radio station broadcast, this is going to broadcast. A multicast is a one-to-many. If we have ourselves or some service like a video service out here and we subscribe to it, it may go to multiple machines. It won't go to all of them because we have this one up here. Whereas if it were a broadcast, it would go to all. And for these, it's only going to go to those who subscribe to it. And then we talk about broadcast domain versus collision domain. A collision domain is a layer 2, and a broadcast domain is layer 3. One of the issues with collision domains is that there's no mechanism to stop layer 2 broadcast. If you get a layer 2 broadcast set up in a loop, it just goes on forever and amplifies itself, and eventually will crash that piece of equipment. A broadcast domain is controlled by a router, so we only go so far. So we want to, if we had a situation, for instance, where we had too much broadcast traffic on our network and it was starting to slow the network down, then we could divide it, and we could divide it here into VLANs. What a VLAN is if we take a switch and we have our switch portion. I'm just going to put dots because it takes too long to try to draw the little squares for them. And we have these ports on our switch. We electronically divide the switch into multiple switches, which we call VLANs, virtual local area networks. In order to communicate among these VLANs, we have to go through a router, and we'll have a 3-interface router here. It will be able to then forward traffic among these different broadcast domains. VLANs are a very handy thing to use on switches. The other thing that it does, if we have VLAN 1, and we'll do 11 and 111, it's because it's easier to make the ones with this thing. 111, and we had another switch out here that had that same set of VLANs. They could be in different physical locations, and the 111 traffic would go to the 111 traffic. We would have these things connected with a trunk port, and a trunk port has all of the VLANs on it. So we can communicate on the same VLANs on different physical devices, but if we want to go between the VLANs, we have to have a router involved in it in some way, a layer 3 switch configured to route or to configure to switch in hardware. In IP addresses, probably going to be the most efficient because it's got more ports. Otherwise, you're going to have to use what's called a router on a stick, where we configure the a router to accept the VLAN traffic. In the IPv4 world, this is the way addresses are set up. I mean, you've seen them before: 192.168.10.1, 10.16.12.3, 172.16.1.1, those kinds of things. And in the beginning of networking, we didn't use subnet masks, and we'll talk about the subnet mask in a minute. It's going to tell us how long the network address is. These addresses, as classful addressing, as you can see here, is broken up into a network ID and a host ID. And we have class A, B, and C. These are the ones that we can use. We also have a D and an F. The D is going to be the multicast, which we talked about, one of the addresses earlier on. And the E is the experimental or reserved area. So in the class A, we have 126 networks and 16 million hosts per network. And if you put 16 million hosts on a network, particularly a Windows network, you're going to have broadcast traffic. It's going to make your network unusable. This is one of the ones that we would kind of want to break up into smaller parts. The class B, we have a network ID that uses 2 of the octets for network and 2 of the octets for host. And this one up here obviously uses 1 octet and then 3 octets for the host. And then we have class C. Well, I'll go back to class B. 16,384 networks, 65,534 addresses on it. And these are the address ranges for the different classes. For class C, we have 3 octets, 3 numbers for the network address and 1 for the host. So we have 2 million networks and 254 addresses on each of those networks. We also show some numbers here, and these are the binary numbers in the front end of this thing. If the address in binary starts with a 0 in the first octet, the most significant bit, then it's going to be a class A network. If it starts with a 10, it's going to be a class B, and if it starts with a 110, it's going to be a class C. Class D would be a 1110, and class C would be a 11110. So we can then have class full addresses. And when we do, and we'll look at subnetting here in a minute, when we do subnetting, what we will normally do is start out with the original subnet mask of whatever the classful is. The classful subnet mask here would be all ones in the address. Going to be 255.0.0.0. This one will be 255.255.0.0. 255 is all ones in the 8 positions. So what the subnet mask tells us is how much of the address is the network ID, 255, 255, 2550. When we start out with the ones in the subnet mask, we have to go continuously with ones until we get to the host's addresses. And once we get there, we're going to have a series of zeros. You cannot mix the ones and the zeros of these things. And these are class D and class C, 224 to 239, and the experimental reserve starting at 240. These private address ranges are not routable on the internet. These are the ones that you can use on your private networks. The 1 or the 10 address range, the whole 10 class A address, so you could have the 16 million addresses on a single network if you could do that. Typically you're going to have to break that down into something else, and we'll look at how we do that in a few minutes when we talk about subnetting. And then we have the 172 range of class B, 172.16 to 31. And when we do that, we only have, 16 addresses in there, which means that when we go with the subnet mask, we're making modifications here in the second octet. So the first octet is going to be the 255, and then we have 16 addresses. 2 to the something power, 2 to the 4th power is going to give us the 16. So we are going to use 4 bits for the network address in this thing. So it's going to be 255, really a pretty bad 55, huh? 255.240.0.0 would be the subnet mask. Let me bring in a spreadsheet here. Maybe that can help me out a little bit. When we do the addressing, we have the IP address, the subnet mask, and then we can calculate things down here, which we'll look at in a few minutes. Actually, we can go ahead and talk about them. The addresses, we had the 10 address of 192. The one that we had was 172, wasn't it? So let's see if we can write it in binary. 128. Too many, huh? 172.16. That won't work. 172.16. And then we can 0.0, and then we want to go to 32. So when we do this thing, we want the network address to be 16, so we have to put zeros in all the other host bits to tell it that these are now host bits or host address bits. So the 172.16 and the subnet mask, when we do the 4 bits, winds up to be 240, and we'll do the other things here in a couple minutes. So we have the IP address and the subnet mask. The subnet mask tells us how much of it is going to be network and how much of it's going to be host bits. So we have those things, 192.168, and the whole 255.255, the whole 192.168 address range. It's masked as a B, and we can then mask it as a C to break it up into smaller components so that we don't have the 65,000 addresses on one network. 169.254 is a special address that Microsoft uses, and it's called the PIPA Automatic Private IP Addressing, and it is used when a computer gives itself an address, and the computer will give itself an address when it's set up to automatically get an IP address and can't find the server, which is called the DHCP server, to actually give it that address. The private addresses up here we said are not routable, and they're not routable. In order to make these things usable on the internet, we use a process called NAT, Network Address Translation, or a proxy server. And what we're going to do is take a NAT device, we'll call it here, and we'll come up with the private addresses, and then we will have a series of public addresses over here that we do a one-to-one mapping of the private addresses to the public addresses. This thing then goes out to the cloud, horrible cloud, goes out to the cloud to get the information, brings it back, goes back through the NAT map, which is on the device, and sends it back to the original machine that asked for the information. NAT requires a number of IP addresses because it is a one-to-one correlation, a one-to-one mapping of IP addresses. A process that we use at home, or at least I use on my router, because it's only by one IP address, is called PAT, which is Port Address Translation. We use a single address out here, but we map it to different port numbers. And if we put an IP and a port together, an IP and a port, and I'm never going to be able to write port, we get a socket. It's called a socket, which is going to be a connection. Actually, maybe I'll be able to write port. Maybe I'll get better at this one of these days. And when we do this, it's going to be a socket. S-O-C-K-E-T. So that's what, horrible job there, huh? What we get to. A proxy server is like a proxy. If you have a proxy, it's somebody that does something for you. So what a proxy server does is we have a machine here that's running a proxy. We send our information to it. It deconstructs the packet that we send. It reconstructs the packet and then goes out to the internet to get the information. And over here we would have a private address, and over here we'd have a public address, so that when it goes out, it can actually get the information off of the internet. A couple of ways to, one, overcome the private public problem with not routable addresses. Also a way to help overcome the we don't have enough IPv4 addresses to go around in the world, and that's where IPv6 comes in. That's the topic of a different one. Subnetworks is when we split up the broadcast domains, and we talked about these things. Let's go back here a little bit. We have 16 million addresses, 16,777,000 addresses in a Class A network, 65,000 of them in a Class B network. What we might want to do is to make these things smaller. I want to see if I can get back to what we had earlier, because I think that the Class C's are a little bit easier to see what we're doing things with. The arithmetic's certainly easier to do. So we have this Class C network 192.168.12 and the subnet mask here telling us how far that we go with it. So we can extend the subnet mask over here and break these things down. Let's say that we needed 14 networks. We wanted to break this thing up into 14 networks. By using our bits, 2 to the n, 2 to the first would be 2, 2 to the 2, 4, 2 to the 3, 8, 2 to the 4, 16, and that number just happens to work out for us here. So we can extend the subnet mask. Now right now we have 8 bits for addresses. So if we extend the subnet mask to the 4 bits, we have 16 different IP addresses in this thing, or 16 different networks in this thing, and we have 4 bits for addresses, going to be 2 to the 4th, there will be 16 addresses on each of them. So if we needed more addresses on them, we'd either have to have fewer networks, or we would have to break it up into what's called variable length subnet mask, which we don't have equal number of addresses on each network. When we do this thing, we're going to lose 2 addresses. By definition, well, let's go to ANDing. When we have a subnet mask, we AND 1 and 1 is 1, and 1 and 0 are 0, and 1 is 0. So when we AND these things, 1 and 1 is 1, 1 and 1 is 1, 0. We're going to get, in the first 3 octets here, nothing's going to change. In the last octet here, we're going to have subnet mask. So if we AND these addresses, and let's say that we start out with a 0 subnet, all zeros in here, and we AND it 1 and 1 is 0, we're going to get the 192.168 dot. Should be, what have I got? What did I do? Oh, a 2 instead of a 1 there. So 10.0, we'll use the 10 network. 10.0, and then the first series of numbers is going to be all zeros. That's called the zero subnet. The broadcast address, by definition, the network address by definition is the one where the host bits are all zeros. The broadcast is where the host bits are all ones. So the broadcast address here is going to be 192.168.10.15. And then the first address is going to be the network address plus 1. And the last usable address is going to be the broadcast address, which is all ones, minus 1. When we take that away, we'll have this, which is going to be 14. You can't use the address where the host bits are all 0 or the host bits are all 1 because those are specially defined as broadcast and network. If we go to our next address, we would add 1 to it, and I'll just do this 1. And we go down, so we're going to add 1 to all these things. So the next address, next network would start at 192.168.10.16. The broadcast would be 10.31. The first usable address, 17. The last usable address would be 30. And you can keep adding ones to this 1 and 1 be 1, 0, and keep changing it to see those things. Those would be the usable addresses. We've increased the number of bits in the subnet mask and decreased the number of bits in the host address. So you get more networks but fewer hosts per network, and you also lose the 2 addresses on each of your subnetted networks. And that's the way that works. And then we're splitting broadcast domains. We reduce the broadcast traffic to improve performance. And we can create VLANs at layer 2, we talked about a little earlier, and map each VLAN to a logical subnet ID. Where we broke that one up, that we could have had 16 subnets with that one. If you need fewer bits to taking away, and as you take away fewer bits, you're going to have more addresses on each of the subnets that you have remaining. And we identify physically distinct networks as logically separate. And this is in the switch. Join the segments with different topologies, Ethernet, token or token ring, and when we join the segments, the separate logical segments, we have to use a router to do that. Map each of the segments to a logical subnet IDs, and when you make VLAN numbers, sometimes it's easier to number the VLANs based on whatever the network address is. It helps you when you're working on it as you get into the weeds as to what's the network address of this particular subnet. If you've numbered the subnet that way, it just makes it a little bit easier to do. And then we assign a subnet ID to each WAN link. Create logically distinct zones for security and administration is why we would want the subnet. We're going to break up broadcast domains is one reason, and to make it more difficult for people that shouldn't be able to see traffic to get there. It's a lot easier to see traffic on the network that you're on. It's a lot easier to compromise the network that you're on instead of one that is farther away. A typical subnet design, we have the VLANs here, 10 and VLAN 20, and they use, you notice they use here 1 and 2. They didn't use kind of what I had talked about, but 1 kind of goes with 10 and 2 kind of goes with 20 so that you know which one we're on. Each of these have a 24-bit, and this is the CIDR notation. /24 means that we have 24 ones in the subnet mask, which is going to be 255.255.255.0. It's masked as a Class C network, even though if it were Class full, it would be Class A. After we got to the point that we started using the subnet mask to designate how many bits are in the network portion of the address, the class really doesn't mean all that much, except on a few routing protocols like RIP, which don't recognize classless. So on these things, we can break this up, and on the switch we have 2 VLANs and we have a router here. and you notice it's got a special color. This tells us that this has got to be a trunk port, because when we put these VLANs on the switch, they get tagged, and they get tagged with their VLAN number. And the VLAN number goes right in the middle of the layer 2 packet. And so when we do that, it's not a standard packet. In order for the router to be able to handle that, it's got to know it's a tagged packet. If we were going from one of these subnets to the other, the traffic would go into the switch, into the router, back down the trunk port, out the router to the next VLAN. But we do have to have a router in order to do those things. If we had a layer 3 switch, we would just plug each of these into one of the ports and tell it to route with a layer 3 switch. Different devices, different hardware operate a little bit different thing. So we've already kind of talked about this. I guess I jumped the gun on it, but the default subnet masks we talked about, 255.0.0.0 and 255.255, and then the 3255s. The binary equivalents down here of those particular numbers. And a custom subnet masks, we might modify the default mask. When we write an address, if we wrote a 10 address, anything from 1 to 126, we would use a starting mask of 255, and then we would extend it in order to make it have more network addresses, subnet IDs, and fewer hosts per subnet. And this little image down here we kind of already talked about, and that's what we did in the example that I jumped the gun on. We extended the subnet ID and decreased the number of bits in the host ID, so that we have more networks, more subnets, and fewer hosts per network. And all the reasons are as before. Classless addressing, as we forget about the address class, except to start with. The starting IP address would then be whatever the classful subnet mask was. The network prefix is still represented as a subnet mask. The subnet mask tells us how much of the address is network. And we need to know that, and then we can break it up from there. Can be written with a slash notation called CIDR, and the class A, the 255, would be /8, /16, /24. What this tells us is how many ones are in the subnet mask. The subnet mask starts at the far left and goes to the right. The zeros, once you get to zeros, you've got to have zeros from there on out. You can't mix the ones and the zeros. You can't have a subnet mask of 101, because this is going to be a string of ones, again, that tells us how much of it is network address. Consider in the addressing scheme whether you need a public or private addressing scheme, and we talked about NAT and proxy servers. That's the way to extend or to make your public addresses go much farther. And how many networks do you need? How are we going to break the system up? And how many subnetworks do you need? How many hosts per subnet? And that's going to be the real question. You can specify how many networks you need, or you can specify how many hosts you need. You can't create addresses when you do these things. It still all has to add up to the number that was available originally. Talk about addressing rules. A network ID can't be 127. 127 is the loopback address for testing, 127.0.0.1, which is technically part of the class A address space. Actually, it would be the, it is in there. The network and the host IDs can't be all 255, all ones in the binary. That's the broadcast address, and it can't be all zeros. That's the network address. And each host ID has got to be unique in the subnet, otherwise we're going to get a warning, and it'll shut down the NICs on both of the machines that we have two hosts with the same IP address, duplicate IP addressing. And typically what happens in duplicate IP addressing, both of them get shut down, so neither of them can go anywhere. If we use static addressing, yeah, you may actually wind up doing that. But dynamic addressing, maybe, maybe not, typically not. And if you do have one, you just need to go back and get a new, and tell the system to get a new address with a renew command. The network ID has to be unique. And on the internet, if you're using a public addressing scheme, you'll be assigned IP addresses. You need to be careful when you put those in. For those of us who use cable modem, my cable modem automatically gets an address. Anyhow, the addresses have to be unique, and if we're assigning them internally with private addresses, they all have to be unique on each of our networks or subnets, and actually networks wind up being subnets. We just call them networks if they're classful. Start out with this thing. So planning the addressing scheme is what we said earlier. How many subnets are needed, and it's got to be a power to 2. We can't say, okay, we need 7 subnets. 2 to the 1, 2 to the 2, they have to be a power of 2. 2, 4, 8, 16, 32, 64, 128, 256, 512, on and on and on. It has to be factors of those. And the addresses, the subnets that allow for sufficient hosts, and the number of hosts is 2 to the n. How many bits are in the host? The n is the number of bits that are in the host portion of the address, where the subnet mask is all zeros. -2, and the -2 is the broadcast address and the network address, the one where it's all zeros and all ones. We can't use that. It's work out the subnets and deduct the least significant octet in the mask from 256 when we do those things. The lowest subnet value or higher. Work out the host ranges for each subnet. Take the subnet address and add a binary 1. For the first host, we've already looked at that. For the broadcast, take the broadcast address and subtract 1 to get the last address for it. Classful addressing not sustainable. Supernetting. Let me bring this spreadsheet back in. I'll see if we can make one of these things work. What I've done here is have a series 168 through 175. Can we make them all be on the same network address? And if we go back here, we're going to need in the subnet mask zeros to make it the networks. And if we go back here, are they all on the same network here? 1 0 1 0 1 1 0 1 0 1. All of these under the ones, this portion are 1 0 1 0 1. So we've now made all of these addresses part of the 7 8, and that works out 8 of them. All of the on the same network, because under the all ones in this octet, they're all on the same network address. So the network address will be 192.32.168.0, the very beginning. The first usable address, we would add 1. The broadcast address is going to be the last one in here with a 255 in the all ones in the host address. And if we put this in here, we have 192.32.175.255 will be our broadcast address. So the last usable address would be the 254. A lot of addresses here. If we need to make bigger subnets out of smaller subnets, we do supernetting. Subnetting and supernetting in each of the instances, you'll notice, is just a matter of modifying, manipulating the network ID, the subnet mask. So in this one, how many, if we use CIDR, this /24//21. You notice that we don't lose as many addresses. We only lose 2 because we've made a larger network. On subnetting, for each network, we're going to lose the network address and the broadcast address. Multicast, the IGMP protocol, manages those memberships. To do multicast, you have to sign up for it. You become a member of a multicast group, and then you are able to see whatever is being sent out from the multicast service at that socket, at that IP address and port number. And it allows the IP host to report multicast group memberships. Routers kind of take care of this for us. And the multicasting requires a NIC switch and a router support. Each of those devices has to support multicasting for it to work. The address ranges are 224.0.0 to 224.255, reserved or well-known. A lot of the reserved well-known multicast addresses are going to be for routing protocols that routers use at the higher level protocols, OSPF and EIGRP. They use multicasting to send those addresses. Microsoft uses, in the 2012 server, 2008 server also, I think, uses multicast in order to install the operating system from the server itself, where you boot to the NIC and then you can install the operating system. It has a setup that you can set it up to do a multicast. That way each of the systems don't have to have individual connections, and I didn't say that earlier. That's why we do multicasting, so to avoid so many individual connections to a source host, so that what we can do here is allow each of them to subscribe to the multicast, which is kind of like a small broadcast or a smaller broadcast, send the information to only the users that want it. Maybe it's kind of like signing up for a mailing list, and we get that information. So in the review, we talked about distinguishing unicast, broadcast, and multicast addresses, and we looked at one-to-one. The broadcast was the host bits all 255, and then the multicast addresses started with a 224. They started with a 1110 in the most significant digits of the IP address. Understand IP addressing schemes. We talked about address class is, subnetting, supernetting, and then the CIDR notation. The CIDR notation was just a / and the / the number of bits that are in the IP address or in the subnet mask. Remember, the number of bits in the subnet mask is the thing that tells us how many bits are network address, so that we can know that the rest of them are going to be host addresses. And we find out how many host addresses by the number of zeros, 2 to however many 0 bits are there, minus 2, because we can't use the network address, the all zeros, and we can't use the broadcast address, the all ones. We looked at the private IP address ranges were 10 with a 255 subnet mask, a 172.16 with a 255.240 subnet mask, and 192.168 with a 255.255. Typically, we'll take the 192.168s and say, oh, those are Class C because it's in the full Class C range, and we'll mask it instead of with the 255.255, mask it with a 255.255.255. So we've already immediately know how to do subnet masks because of the way we do those. We just extend the number of bits that are in the subnet mask. And when we do that, instead of going from the 65,000 whatever plus addresses that were in the Class B mask, we're going to the 256 minus 2, 254 usable addresses in the Class C masking scheme. And then configure an IP address scheme for a private network, breaking them up, and configure the IGMP multicast groups. We know what an IGMP multicast group is. So with that, I'm going to stop this one and hope it's been useful.